Have you ever just stopped and wondered how an AI can look at a digital photo, which is really just a chaotic grid of millions of colored dots, and somehow instantly find a human face? I mean, how does it make any sense of that complexity? Well, the answer isn't just about throwing more computing power at the problem. It's about a surprisingly elegant and honestly beautiful idea that hidden inside all of that noise, the data has a secret shape. So how do we get from a million pixels to a single face? Here's the path we're going to take today. We'll start with the sheer scale of what we're calling the million pixel problem. Then we'll get into an unexpected answer and figure out what a manifold really is. After that, we'll see how this becomes the AI superpower. And finally, we'll look at the final proof that really brings this whole idea home.
Okay, first things first. To really appreciate the genius of modern AI, you have to get your head around the massive scale of the problem it's trying to solve. It's a challenge so big that it's often called the curse of dimensionality.
I mean, think about it. A single high-resolution photo is an absolute ocean of data points. So how on earth can any algorithm navigate that ocean to find one specific thing, like a face? The number of possible combinations is just astronomical. It seems like it should be totally impossible to search through.
And this is where it gets really mind-bending. You see, every single pixel in an image can change. It has a degree of freedom. So a 1000 by 1000 pixel image isn't really a two-dimensional thing, not to an AI. It's a single point in a space with 1 million dimensions. That's what you're seeing here. It's a space so vast, it's pretty much impossible for us to even imagine.
So how do we solve this? Well, the solution isn't just about building a faster computer. It actually comes from a really fundamental insight about the nature of data itself. A hidden, elegant structure that makes everything much, much simpler. And here it is. This is the key insight. The manifold hypothesis. It basically says that even though the space of all possible data is ridiculously huge, the real-world, meaningful data, like pictures of actual faces or recordings of human speech, it doesn't just fill up that whole space. Instead, it's all concentrated on a much simpler, lower-dimensional shape, called a manifold, that's just kind of floating inside it.
Okay, I know. That definition sounds incredibly academic, right? A low-dimensional manifold embedded within a high-dimensional space. But trust me on this, the core concept is surprisingly intuitive. All we need is a simple, everyday analogy.
So let's make this really simple. We're going to forget about data for just a minute. To really get what a manifold is, all you need to think about is the difference between a flat map and a globe. So a flat sheet of paper, that's what mathematicians call Euclidean space. It's simple, right? The shortest distance between 2 points is always a straight line. But our planet isn't flat. The surface of the Earth is a manifold. If you zoom way in on your neighborhood, it looks flat. But globally, we all know it's curved. The shortest flight from New York to Tokyo isn't a straight line on a flat map, it's a curved path over the globe. And that's all a manifold is, a space that looks flat up close, but is actually curved overall. Okay, so let's bring this back to our photo problem. Remember that million-dimensional space? It contains every possible combination of pixels. And yeah, most of it is just meaningless static. But now let's think about only the images that are actual photos of Albert Einstein. All of a sudden there are rules. The pixels can't just be random noise anymore. They have to form his eyes, his nose, that iconic hair. These real-world constraints dramatically reduce the degrees of freedom. All the valid Einstein pictures clump together, and they form their own small, lower-dimensional shape, their own manifold, inside that gigantic space of random static.
So this is cool, but how does this one idea give AI its superpower? How does it turn what seems like an impossible task into something that's totally solvable?
Well, this hypothesis is basically a cheat code for machine learning. The algorithm starts with that messy, million-dimensional dataset, but it makes one powerful assumption. The data I actually care about lives on a simple, hidden shape. And its entire job then becomes learning to find that shape. By doing that, it can pretty much ignore all the useless data, all the noise, and focus only on the few key features that really define what it's looking for.
And at the end of the day, that's what this is all about. The manifold hypothesis is the core assumption that explains why modern AI is so incredibly effective. It's the reason algorithms can sift through these unimaginably large datasets and find the patterns that matter. They aren't trying to map the whole universe of random noise. They're just learning the simple, elegant geometry of the real data.
But here's the really cool part. This isn't just some clever idea from an old textbook. The manifold hypothesis is something scientists are actively exploring and trying to formally prove right now.
For decades, this idea was mostly just accepted because, well, it worked in practice. But as this research timeline shows, the work to formally explain it is absolutely cutting edge. A new statistical model was proposed back in 2022, and the latest version of that research was just published. So we're actually moving from just knowing that the data has a shape to understanding why that shape even emerges in the first place.
And I absolutely love this quote from the researchers because it just gets right to the heart of it all. What they found is that this complex, hidden manifold structure isn't magic. It can emerge completely naturally from a remarkably simple statistical model. It suggests that the shape of data is a really fundamental property of the universe, not just some weird coincidence.
And this leaves us with a pretty provocative final thought. We now know that images and sounds and language, they all seem to have this hidden, simpler geometry. So the big question is, what's next? If all this data has a shape we can discover, what other secret structures are out there hiding in plain sight, just waiting for us to find the right way to look?